proper number of particles for some altitude into the program. And we verified the mean free path by tracking each successive molecule collision, and we found that the mean free path is correct for the altitude we're at.
So one of the applications that we did with our model was modeling supersonic movement. And what we did is we simulated a box moving at supersonic speeds through the upper atmosphere, and when it will form a shock wave, and the shock wave will have an angle theta between the shock wave and the normal to the box, and it's given by the relationship sine of theta equals c over v, where c is the speed of sound and v is the speed of our box. And from this, we can find that theta will actually decrease with a faster object. And here are two results that we have. First, we ran it at Mach 1.5, and as you can see, our angle is 41.8 degrees. And this does match with the mathematical calculations, so it proves that it is working correctly. And we ran it again at Mach 1.75, and we got a smaller angle. So this shows that our simulation is correctly calibrated for shock waves.
And you notice that the dense region here more correctly fits this line than the dense region here, and that's because there's boundaries here. I put specular boundaries on the sides so that you wouldn't have vacuum on the sides and everything would like fall out the sides. And so if I had a bigger computer, I could simulate the region out to there, and then we'd have a perfect shock wave. But since I have only a quad core, then I can only do this much of it, and it kind of gets blown over a little bit, so it doesn't match quite as much. Another test we did was we looked at the force exerted on the object when molecules collide with it. So we measured the momentum change for all the molecules that bounce off some barrier. And we wanted to see what the difference in, like aerodynamically, was between a blunt box and a pointed box. And we found that it's almost exactly the same, because this one, it's blunt, it's less aerodynamic, but this box has a larger area exposed to the oncoming gas. And so essentially they experience almost the same drag. This one was just a little bit smaller. But we can apply this method. We can always print out how much force was exerted if we're going to model something entering the atmosphere. And that would be really helpful to know. Now when I put this on the quad core, something that's nice you can do on the quad core is you can change the regions that are calculated by each core. So essentially each core gets some number of cells to calculate, and we want to pick cells where molecules move within the cell rather than across the cell, across the cores more. And we time how long it took for each core to calculate its section. And if we see that there's some area that's more compute intensive than the others, then we can move these boundaries. And that's something that if you were using a supercomputer, you probably wouldn't do, because then you'd have to send all of the data regarding those cells that you just changed processors to the other processor, and that would take a lot of time. So that's one good thing we have about multi-core processors. In the multi-core program, we initialize all of the molecule positions, velocities, and we put them in their data structures. And then the multi-core part, we initialize all the threads, and each computer calculates collisions and movement for molecules within its cells. And then it also moves molecules that move between cells within its region. And all the single core has to do is move molecules that move between cores. So we're syncing after every time step, but the single core part is almost nothing. It just runs through this array. And since the final report, this is what we had at the final report. I've restructured some of the code so that we're more efficiently using CPU power. And I mean, at this time, this is almost completely calculation. This is also a little bit of memory movement and stuff like that. But you can see we're very efficient in our use of CPU. But once I figured that out, there became this problem with memory access. And as it turns out, this was not what I was expecting. There's a bottleneck for memory on multi-core, which is really annoying because every core has to go through the same memory bus to get to its data. And so while we have plenty of compute power available, if you have a data-intensive program, which a lot of scientific applications are, then you pretty much have to deal with this memory bus problem if you're using multi-core. And I measured this by looking at the time to calculate a single molecule-molecule collision. And you see, when one core was doing it, it took 2.1 microseconds. And when 2 cores were doing the same calculation, each core took 2.4 microseconds about. So because they had a shared memory, they took longer. And with 4 cores, it was 3.5 microseconds. So it really slows it down in terms of memory.
Intel's solution is to add more cores.
No, they should add more memory buses.
No.
That's what I want.
You're right.
Are you threaded here and not NPI on the?
This is multi-threaded, yeah.
Okay.
Traditionally, the slowdown would become when you need to access memory from another, but each processor in this setup would have direct access to its own data, which is really nice. So here's our speed up analysis. The green line is what we had at the time of the final report. The orange line is the one I got after I completely rearranged the data structure. And obviously, that's only 2.5 to 1 or so. It's not 4 to 1. But you notice that when we factor in that slowdown you get from the analysis of how long each core took to run that one section, we do get linear speed up, and it's 4 to 1. So if we didn't have this memory problem, we get great speed up, but we have the memory problem. So now we're going to do the demo, which should be finishing up right now. Oh, it finished. Cool. So let me find. So here we have our output. This all is the momentum change calculation I was doing. And then up here you notice we had about 61 million molecule-molecule collisions. This is why it took so long. And we have the maximum number of particles in each cell was 65 particles. That's quite a bit. Total time, 864 seconds. That's about 14 minutes. This is a program, I cut the time by like a third. It's something I would never put in data because the particles haven't had time to form a constant stream, so it's going to look really spotty and it's not quite correct. I also fussed with some of the parameters so it runs faster. But anyway, here's the data we just got. We're running an accommodating boundary with the spacecraft shape. And you notice this is the dense region. This is a density map. And it's kind of, it goes away from the spacecraft a little because the accommodating boundary sets molecules in all of the different places. And you notice that when we look, this is a specular boundary with the same shape. You notice all the particles come in and they go off. And so you get a totally different look to your density map. And that's why it's really important to have both accommodating and specular. Because,
show both again?
Yeah, I'll toggle back and forth. Because if you had a satellite coming in, then like this actually affects satellite decay patterns, where if your satellite has been out in space for a while, it'll start hitting the atmosphere and it'll look like that, but slowly it will accumulate molecules and go to something more like this. And so we need to take both into account. And it's also good to take the drag into account. So I'm just going to go and show you how this starts. Okay, so it's setting up all the data structures, and this is what's interesting.